Okay. Yeah. It's my pleasure to have today Nayara Fonseca. Nayara did her PhD at the University of Sao Paulo under the supervision of Gustavo Ullmann, mostly working on physics beyond the standard model, model binding and phenomenology. During her PhD, she had the opportunity to be a long-term visitor in different institutions, and she visited the Center for Theoretical Physics at MIT, hosted by Jesse Thaler. After her PhD, she worked as a postdoc at the DC Theory Group in Hamburg, working on particle and cosmology. And after that, she was a postdoctoral fellow at the ICTP in Trieste. Last year, after she moved to the UK, she spent about a month at Queen Mary University of London. And next month, she's joining IBM Research UK to work on topics connecting physics and machine learning. Nayara, whenever you want, go ahead. Thank you.
Thank you, Ernesto. Thank you very much for the invitation. I'm going to talk about phenomenology of deep learning. This is quite a new topic. Actually, this field itself is under construction. And I hope I'll be able to share my excitement with you about this. And also I hope that this is useful for people that don't work on machine learning, but also for those that already work on machine learning applications. And I hope I can give you some different perspective of the field. So let's start. Okay, so we all know that machine learning applications have a very successful and long history in physics. And I tried to find some kind of paper about high energy physics in the old days. And I found this one here by Kyle Kremner. That's nowadays, probably you know, he's very well known about his work in machine learning, high energy physics. But at this time here, I guess he was a student. And he presented this work in this workshop in application of neural networks. And then he says that, neural networks have become quite common in high energy physics. They first appear in the literature for the use in Trigger and other online applications. And then he cites this 16 reference, and this is quite old, as you can see, right? So this is like more than 30 years ago. So then you may wonder what's happening now, right? Why there is this explosion of machine learning applications in physics and actually in the sciences in general, right? In the last few years. And basically the answer is like scale and complexity. There was like exponential increase in computing power in the last years. And here I put these two illustrations that are actually old for machine learning standards, but just to give you an idea that on the left, we have like the data size, the number of samples or your data set as a function of the years. And these different names are just machine learning benchmarks. So you see that this is getting bigger and bigger. And on the right, I have the number of neurons that you can think about. This is just like the number of parameters in your model. And these numbers are just different machine learning models. And then you see that we are getting closer to the human level, at least from the point of view of number of parameters. And I will certainly will not be able to review all these literatures, and I will not be able to do any justice to all this. So I will just cite these reviews here that are really nice. And the top of the talk today is actually the other direction. I'm going to talk about the theory of deep learning. And really my goal here is to show that there is an enormous gap between what's known, what we understand about deep learning and about the applications that are amazing. Since there are like a community of mathematicians that are able to prove theorems for very small networks that are really not used in practice. And in the other side, there are this like big community of machine learning practitioners that like they are using state-of-the-art machine learning, but actually they are using everything very like in an empirical way. And I think there is a big room to be like physicists are very good at connecting theory and data. So I guess this is a really, really like a good place that physicists could fulfill. And we know that sometimes we use models that are not that vigorous. Actually, many times, right, we use models that are not that vigorous, but they are still very useful. And this is the theme of this talk. So this direction here. And so this is the plan for the talk. I will start with a very informal introduction about learning and in a very informal way. And then I'm going to tell you why I think we as physicists should care about this. Well, this is a personal view. And then I'm going to discuss some intriguing deep learning phenomena that appeared recently. And then at the very end, I'm going to discuss some recent work with Veronica, where we are working on similarities like contrastive learning and generalization. Okay, so what is learning? So as you know, learning theory is like a very formal field. Like this is a whole field. But let me give you like a very informal and phenomenologist attempt to define this. So learning is just the ability to find rules, right, based on some data that we have access to, that can be consistently applied to unseen data, to new data. And this model of our control universe can be describing a natural phenomena, right? A theory that describes experiment, but it can also be described artificial phenomena, like a neural network model that recognizes images. The most important thing here is that to be useful, to make any sense what we're doing, this model should be able to predict, like with some appropriate accuracy for this problem in question, like the outcome of new data. That's it. And let me give you one concrete example. People probably that work on this, they already know this, but just let me give you a very simple example. This is the Siamese database, right? It's the Hello World in machine learning. That's just a very large database of handwritten digits with labels. So we have like the pixels, and then they have the proper label. And the task here is that we want to get from this data, some program, some function that can recognize digits. So in other words, what we want a function that takes this table of pixels in grayscale and is able to tell me, okay, this is a 9. So as you can see, this is the type of program that is very easy for us as humans to solve, right? This is a kind of a weird 4, but I mean, we know that this is a 4. But if I ask you to code this, to give me like a code, a list of instructions, what's the concept of a 4? This is gonna be hard. This is a complicated task. And this is exactly the kind of problem that is good to ask a machine learning to do for us, right? We want to give like an input that's in this case just this table of pixels, and I want a function that in this talk is going to be the neural network that is able to tell me that this is a 9 with some accuracy. So let me just zoom here in the function. So what is then a neural network? It's just like a very specified way to construct this function. It's just like I have the collection of rules, and I could do this in many ways, and the neural network is just a receipt to do this in a very specific way. So let's remember just like this notation. So here I have the X, that's just the input. So in the case, it's just like this table of pixels in this example. And this is just like a way to represent different layers. So these W's are what we call weights. And here we just contract this input with these W's. So this dot product here is just like a weighted sum. And this is the argument of a nonlinear function. And this function is activate or not activate, just borrowing like semantics from biological neurons, depending on the value of this B, that's just we call bias. So just to recap, we keep doing this, right, recursively, and this is the answer. This is the output. So what the neural network learns then is just the output function, this fx, by building complex representation on the top of simple ones. So here in this cartoon, we have this very clear, right? So this is the image, the neural network first recognizes the colors, and then as we go deeper and deeper in the layers, it's able to recognize more sophisticated features until it is able to classify car, person, or animal. So let me give you just a bit of notation for the talk. In this talk, when I say deep learning, I just means neural networks with many layers. just this. And the depth for me is like just the number of layers. So here I have 3 layers and 1 output. And when I say width, I just mean the number of parameters at each layer. Here I have like 2 parameters, 2 nodes, or 2 neurons in this first input layer. Okay. So now the important question, why we as physicists should care about all this. And well, as physicists, we are told that more parameters is just something terrible, right? It's really bad. If I want to have a theory that's beautiful, elegant, I should construct this with a small number of parameters. And there's this very famous quote by Fonseca that says that with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. And this actually apparently was done in this paper. People have done this. However, well, neural networks are not very worried about what we think it's elegant or beautiful. They are highly over-parameterized and they are just doing fine. So when I say over-parameterized here, just means that the models have much more parameters than data. And let me just give you one example. Here, let's suppose that I want to fit these red dots, right, 11 dots. And I want to fit this with something that's called ReLU networks. So this is just like a prototype of a neural network with 2 layers, and 1 layer is no trainable. So it's something that's very simple, a very simple network. And first I try to fit this with like 3 features. That's just like 3 parameters. And this looks quite bad, right? When I have 30 parameters that they call here the overfitting regime, right? That I'm slightly above the interpolation threshold. This is super bad, right? I just go over all the points. It doesn't seem that is generalized at all. However, if I try to fit 11 points of 3,000 parameters, this is smooth again, right? This looks quite good. And this is going to be the kind of phenomena that we're going to study next. So I'm going to discuss 2 intriguing observations. The first is an experiment that is called the random label dataset. And this is a very influential paper in machine learning that's called Understanding Deep Learning Requires the Thinking Generalization. And we're gonna do this experiment together. And in the second part, I will discuss a specific phenomenon that's called the double descent that tries to reconcile modern and classical machine learning. Okay, please interrupt me at any time if you have any questions. Okay, so let's do this experiment. So let me say that this paper is actually a classical, you can say classical machine learning paper from 2017. And actually they put updated version last year, basically saying that nothing changed much. I mean, from the theory side, that's why they include just this still requires the thinking generalization. There are a lot of progress from the experimental point of view, but not the theory side indeed. So let's see what they do. So suppose that I have this data set, right, with images, and they have proper labels, right, dog, pizza, cat. And what we're gonna do, we're going to randomize, completely randomize this label. I just mess up with the labels uniformly, right? So here, for instance, I have pizza, and pizza, of course, they share a lot of features, right? They are pizzas, but here, like now pizza, it's dog, and another pizza, it's cat. So they are completely different classes. So why we want to do this? This is because now this data has absolutely no structure. So if I take a neural network to fit this data, I'm basically fitting noise. Basically, I'm indeed fitting just noise. And this is good because now I can measure the effective capacity of the neural network. So if I take a neural network to fit and to explain this with 100% of accuracy, this means that the neural network is just memorizing, right, the entire data set. And by construction, the way we are constructed these, there is no way to generalize, right? If I train a model like this and then I show new data, the answer will be just chance, right? Because there is no way to generalize just because there is no structure. There is no way to follow any reasoning in this. And then they apply this to state-of-the-art convolution neural networks that work very well in practice. So I just put here a big neural network. I mean, you are not supposed to read this. It's just for you to give the scale. And then let me give you one of the results. So here is the average loss. So you can think that's just something that depends on the comparison between the correct label and the predicted label. Okay, the error of your neural network as a function of the gradient steps. So this you can think about like just the time for how long I'm training and repeating this process. And these are the learning curves. So this is the training data. And then remember, for random labels, there is no way to generalize by definition, right? So let's compare the two, like the two extreme cases, true labels, the blue dots here. So for the true labels, we have like a correct label. So you see that, well, the neural network quickly realizes what's going on and just converts to zero error. Fine, no surprising. But you see that for the random labels that are completely like, they have no structure. If I keep training, eventually the neural network also it's able to get zero loss, completely overfits the entire data set. So this means that even if I just give to the neural network enough steps, at some point it's going to converge also. So if this, we can conclude two things. The first thing is that deep nets in the regimes that we use now, they can easily fit random labels. So there is just, if you just say, okay, I have a neural net that have 100% accuracy for the training, this doesn't mean much because basically it can just tell you that this is just like memorizing your entire data set. And another thing that for me, it's actually more important is that usually people just criticize, say, okay, deep learning is just optimization, I think, with codes, because optimize is not something easy. But this is a clear example that this is not the case, because by definition, this setting, I mean, this experimental setting cannot generalize, because I construct in a way that this is impossible to generalize, but it's optimizing very well. I really can get like a zero, exactly like zero loss if I just wait enough time. And I mean, they conclude, right, saying basically that well, we need some formal measures of complexity. We basically do not understand very well the over-parameterized regime. And this is not gonna be just about the architecture, right? Because here they use just a normal architecture network. We need to, this is gonna be for sure a combination of the model, that's the architecture, the algorithm, the data distribution, in order to be able to understand this regime where we have more parameters than data. Okay. If there are any questions, please let me know. Otherwise, I will go to the second part. That's the double descent phenomenon. Okay, so let's start with, let me give you some motivation first. So what this phenomenon is. Suppose that now I'd like to fit these samples, these blue dots. So I have here the model in blue. And I have the true function in orange, right? And I'm trying to fit this in this first frame here with 1 degree of freedom. This looks really bad. I'm just measuring the error with like mean square error. So the comparison between the true value and the predicted value. In the second case, I'm using like 4 degrees of freedom, and now it's almost perfect, right? And almost completely going over the true function. And now in the last painting here, I'm using 15 degrees of freedom. This is quite bad again, and basically it's going over the points. And I really do not expect that if I'm adding new samples, right, new blue dots, this is going to generalize. The samples are not going to be here or here. So let's go a bit deeper on this understanding, right? How do we usually understand model selection? That in statistics we would call this bias variance trade-off, but maybe for physicists we just say common sense. So how you usually construct models? Here in this cartoon I have the error on the y-axis as a function of the number of parameters, just like the, let's say, the complexity of your model. And if I keep increasing the number of parameters with respect to the training set, the training error is going down, right? Like exactly here, right? If I'm increasing like the number of parameters, at some point I can go over all the points and I just have zero error, right? I just go over the points. However, I do not expect that it's a good strategy, right? I expect that at some point, well, I have like so many parameters that I'm going to, or the overfitting regime. I do not expect it is going to generalize. So it should have like a place where I should stop adding more parameters in my model. And this should be the place that this is the, let's say, the correct model. And if I want to compare this with the previous plot, here it would be the region where I have the underfitting regime, right? Here would be the region where I'm already above, like this threshold, I'm in the overfitting regime. And this point that the sweet spot is exactly the point where we try like 4 degrees of freedom. That's the good point where this model has exactly the complexity that minimizes the test error. So this should be the right point. However, what's observed is that deep nets are here. They like highly over-parameterized, and in general, they have at least 1 order of magnitude more parameters than training data. This is there is like overwhelming evidence for this. And what people observe is that in general, if you increase this ratio, like parameters over the number of training points, the test error goes down. And this is kind of bizarre. Like as a physicist, I found this very intriguing and like just makes no sense, right? There should be something wrong. Although basically all the neural networks that people use in practice, they are working in this regime, especially like these language models that people talk about. They have much more parameters than data. And this is quite very intriguing. And people try to come up with some way to reconcile. And there were like many papers, but here I'm just citing the paper that basically gave this name, the double descent phenomenon. And what they say is that, well, actually, this is not the whole story, right? This curve, actually, there is a second piece of this curve. This curve indeed is going up like this, but eventually, when we get to the point where what they call like interpolation threshold, where I just have enough parameters to completely memorize my entire data set, like I just overfit everything, and this actually goes down again. And we just, I could not see this before because we just didn't have computer power to have so many parameters before to run this kind of models. And there was like here, right now, people can explain this analytically with very simplified settings, but for like in the state of the world neural networks, there is no full understanding, and people also don't know what the range of validity of this. Although we use these neural networks all the time, we know exactly what's going on here. And there is like a huge literature, like you follow this paper. I just want to give like one example where they apply this for like really networks that are used in practice. That's this one in this paper. And here they consider deep neural networks. Like they want to investigate exactly the double descent phenomenon for like real life neural networks, and for like image classification, like something very like well known in the literature. They take like well-known data sets and try to observe this phenomenon there. And what they observe is this. This is exactly, we read this as experimental plot. This is exactly, we should call this experimental plot. So we have again, like exactly as before. I mean, remember, I'm always repeating the axes, right? It's just that they have different names, but this is again, oops, the same kind of plot, right? Arrow as a function of parameters. So here I have test and train error as a function of with parameter just means that to the right, I'm increasing the number of parameters of my model. And you see like, and the training curve, it just goes down, right? Eventually I can completely overfit my training data. But actually the tests, actually it does what we expect from the classical machine learning regime, but eventually it also goes down again. And this is what they are calling like the modern regime of machine learning. And this is actually happening like for his net, that's very well known. And I guess here they use probably CFAR data set. So it's something that's very like neural networks in data sets that people use every day, like in normal settings. And something that is quite interesting is that they actually take the same type of model, and they add now noise, which we expect that is present in real data. And they notice that now, if you add noise, what happens is that the peak is higher, which makes sense, right? If I add noise, it means that it's harder to explain, right? The test error is higher. But there is some other thing, right? They actually shifts to the right. This means that the peak, right, of this guy here shifts a bit to the right. So in order to get to the interpolation threshold for a model with noise, I'll need more parameters, meaning that I need like a more complex model in order to explain some data with noise. And this is, of course, very empirical. These papers are all empirical. There is no like a good analytic understanding or like a theoretical explanation for what's going on, but they repeat this for different architectures, different data sets, and they always get this type of curve. And what we did in our work is actually to try to see the same kind of phenomenon, but now in contrastive learning. So now remember here, they are considering image classification where we have predefined classes. So what we want to do is to consider, to try to observe the same phenomenon, the double descent, but in a contrastive setting. By contrastive setting, I just mean like, remember, similar or different is the simplest question I can ask about an image or an object that's not directly related to its features. So it's not the relation, what's important is the relation among the features and not the features themselves. So this is another kind of learning, and we believe that this is genuinely different from learning how to classify. And to do this, we actually consider this type of architecture that's called the Siamese neural network. And this is the simplest setup that you can have to do contrastive learning. And the setup is the following. So I have a copy of the same neural network that shares the same weights and biases. And they're very commonly used to detect similarities, like face recognition. There are more complicated versions of this, but usually in the past, people use this for face recognition. And you have these pairs of inputs like X1, X2. And there is like a bottleneck layer where I basically measure the distance between these two output vectors. That can be Euclidean distance or something fancy. But the idea is that a successfully trained neural network in this setup should be able to say that the X1 and X2 are related or not. And this is really generic, like that's the question, if it's related or not. I don't want to give the rule, right? The neural network has to figure out if this is like, there is some equivalent relation between these two things. And actually you can use, for instance, to know if the same event in a relativistic setting is measured by two observers in different reference frames. That's what these people did here in this work. I just want to give you one example from this paper that's quite nice. So here in this paper, just so you get familiar with this type of architecture, they use a Siamese neural network to study like a Lorentz transformation. So what they do, they have the same kind of architecture that I showed before. And since this is a supervised task, so they have to construct the pairs like X1, X2 with proper labels. So here is just like a 4-vector. And we say that X2 is related to X1 if they are related by a Lorentz transformation. And X2 is unrelated to X1 if they are just like a random combination, a random shifting of the components of the vector. And they label this like with Y0, Y1, and they generate like random boosters and random rotations to do this data set. And then, they train this by minimizing the loss, and they test, and they got like a good accuracy and for training and test. But so far so good, so what, right? I just told you that this network was used to detect like faces, right? So now these people here are using for vectors, that's something much simpler than faces. So this is not surprising that this is good. However, these physicists, they're actually physicists, they realized that they could put a bottleneck layer here. And what they did, they started with like a kind of huge dimension, like they have a lot of nodes, parameters, and they do exactly a bottleneck layer. They force this neural network to compress all the information in one neuron. So I have just one scalar here. So they include in this Siamese setting an extra layer where the neural network has to output just one node, one layer. Sorry, one layer and like one parameter for the one branch and one parameter for the other branch. And then they calculate the difference, right? This they call like, let's say, function from the input 1 and function from the input 2. And they repeat the process, like they do a loss minimization between the difference of these functions and the label y. And then they said, okay, let's inspect what the neural network has learned. And to inspect this, they just use polynomial regression. Right now I have like a scalar, and I also know my input, like I have like time and the coordinates, like X, Y, and Z, and I can just do polynomial regression to recover this. And what they observe is the following. If they force like the neural network to use just a single scalar function to decide if these two events are related or not, the neural network calculates the space-time interval. Of course, if we have to calculate this, it is not gonna do something weird, right? If some slope or in some constant. But when they plot the intermediate output, this thing as a function of the space-time interval, they see that there was like a clear correlation. And when they do the polynomial regression, probably they did in this order, right? Probably they realized there was a correlation, then they try later a polynomial regression, they realized that's exactly the space-time interval that it calculates to decide that these two things are related or not. And to double check that they are doing something that's consistent, they actually now fix the S squared, like they fix the space-time interval for these two inputs, and try to train again. And in this time, the network is just confused. It has like, it just cannot decide. Remember, this is 50-50, right? They can be related or not related. In the neural network, just saying like around 50%. So it just could not find another symmetry, another invariant to decide. So indeed, it's like a clear example, I guess, that there is no ambiguity in determining what is or not interpretable. So let's go back now to my example. Here it's a really high dimension, so it's not like a 4-vector. I have images, so it's harder to visualize. That's why I want to give like a break to, so you have some idea what we're doing. So we are considering images. So this is like 28 by 28 pixels, like in grayscale. And we train this network like in a similar way. We have this bottleneck layer where we exactly are measuring the, like calculating the difference between the outputs, the distance between the images. And we consider like a contrastive loss to train this network. What the contrastive loss does, I mean, let's give like take some idea from this hidden representation. So the contrastive loss try to collapse images that are similar, right? If y equals 1, this term is 0. So I try just to collapse this, maybe make this image together in the hidden space. And if they are different, I mean, this term y equals 0, this is 0. So I just try to pull apart images that are different by a distance m, right? I don't want, if they are different, I don't want to keep pushing them. If they are distanced by a margin, I'm already gonna call them different, and that's it. It's a very simple loss function. And then we study how training and test error vary by increasing like the number of parameters. Remember, right, what I want to test here is the double descent. So I want to keep increasing the number of nodes that I have here, or network width, if you want. And we use different losses, different data sets, and try different branches for the Siamese. This, what I call Siamese branches are just these, right? We try different branches. And then we realized that in this kind of setting, we actually could use two sources of noise. There are two ways to introduce noise. We could, in principle, introduce noise, what we call like single label noise. That's exactly the kind of noise that we also have in classification. And you could also introduce pair label noise. That's a type of noise that just appears if you have pairs. So single label noise, I just take a trouser and suppose I just flip, right, the label here, and I take a trouser and call it a boot. And then this type of noise is going to propagate like everywhere, like the same way in the entire data set when I form the pairs. But I could also, in principle, just take the data set with pairs and just flip the label, right? These two things, of course, are similar, and I call them different. And that is going to propagate in an entire different way in your data set of pairs, right? This is just concentrated here. And then, okay, let me show you one of our results. So again, here I have a test error as a function of neurons per layer. Neurons per layer, again, just like you can think about number of parameters of my model. I copy here again the cartoon from the original paper. So just you see that we have exactly the same type of behavior, right? We have like one descent, the second descent. I will tell you the colors, what the colors mean later. But here, just to see that, okay, double descent appears in Siamese neural networks. This is happening here. It's very clear that it's not really just going up as we expect from the classical regime. Another important information that I should give you from this plot is that here we train with 6,000 pairs. So just 6,000 pairs of images. And for the model that we are considering here, we use like for this particular plot, we use like a fully connected neural network with 3 layers. I mean, the important information is that with 8 neurons per layer, more or less here, you're already in the over-parameterized regime. I already have more parameters on the side of the plot. I already have more parameters than training data. And you see like something interesting. You see, if I could have stopped here, right? I could say like, okay, let's stop here because this doesn't make any sense because I already have more parameters than data as I expect from the classical regime. I will never be able to see that this plot actually goes down again, right, later on. I mean, this model here gets better performance once you have much more parameters. And then let's say the surprising piece is here. So as I said, I could introduce noise in 2 different ways. But what is surprising is that they are distinctly manifested depending on the source of noise. So the black curve is just like no noise. I have no noise. I can also see double descent, but I have no noise. The dark blue is single label noise, right? The first type of noise that's similar to classification. And the second is pair label noise. The one that appears just if I have pairs. And for the same amount of noise, here for this plot, I consider 10% of the random label noise, they basically give you different learning models. You see that in principle, the single label noise start bigger, right? And it's always higher, meaning that it's harder actually for a model to explain this data if I have like single label noise. I mean, we are training all the models in exactly the same way, right? In the same number of epochs with the same learning rate. And the pair label noise actually performs better until the point it actually gets worse. And for in the very deep over-parameterized regime. And this is kind of intriguing. It's really high dimension here, so it's really hard to think about a way to explain this with pictures, but we try to come up with an explanation for what's going on here. And one possible explanation is the following. So here I'm reducing our parameter space of 28 by 20 input to a 2-dimension with, instead of having 10 classes, I have just 2. Let's say that I have a red distribution and green distribution. And I want to split these distributions. And I say that if they are separated by a distance larger than d, I call this different. If they are closer, like my distance is smaller than d, I call them equal. Okay. If I introduce pair label noise in this kind of setting, what I do, I just take like 2 green, right? 2 green samples, and I call them different. And I take 2 that are different and I call them equal. And what the neural network has to do to adapt, to fit this noise, basically neural network has to put this point here. I just basically move this here. And here, by my definition, I already call this just 2 points different. And I have to basically make them together, right? The function has to adapt a bit, make them closer and closer. And then I already call it equal by my definition. However, if I introduce single label noise, what I'm doing, I'm just taking like one sample inside the distribution, one like sample inside of the green distribution and call it a red. So let's say I take one sample, I have a trouser and like a boot distribution, and I take one sample inside and say, okay, now this is a boot. And then the neural network has to do a big gymnastic, right? To be able to fit this noise, right? Like just like we're trying to represent here is just like making a deformation. So it's expected that indeed single label noise makes more mistakes if I want to overfit my training data. So that's what we observe here, right? There in general it performs worse than pair label noise. However, like this is just half of the story, right? This can only explain half of this plot, right? Because I told you that at the very end, the pair label noise actually takes over, right? Just crosses right there, this plot. And you see that at this point here, where the crossing happened, I'm already above like the 98,000 parameters. So this means that I am using 98,000 parameters to fit 6,000 pairs. So I'm really in the over-parameterized regime. And well, this was very confusing, and we tried to come up with another explanation for this. And as far as you know, this has never been pointed out in the literature, this type of noises. And we said, okay, let's take a look at the training error. Here, I mean, the plot that I'm showing you all the way along is the test error. Now I'm showing the training error as a function of the number of parameters. And then since here I'm using like a highly over-parameterized network, I was expecting that this is, I mean, this just 100% has 100% accuracy, because I have so many parameters that I could, in principle, remember the example of the beginning of the talk. I can just go over all the points. But this cannot be achieved no matter how many parameters we give to this case, to the pair label noise. This never reaches zero. I mean, this is quite small, right? But this never reaches zero. And we said, well, what's going on again here? Why I cannot overfit? In principle, we always, I mean, I'm telling at the beginning, you can always overfit, right? At least in the classification example, I can always reach the point where I can overfit completely my entire data set. But here I'm just showing that this is not true for this case. And we actually came up with some explanation for this. We realized that what pair label noise is doing is actually breaking some transitivity in the data set. And let's go very slow here, case by case. And let's say, okay, let's consider now, again, I'm going to reduce a lot the dimensions so things start making some sense. I have two classes. I have like the black circles and the orange circles. And I connect, if they are similar, I connect with a green edge, okay? If they are different, I connect with a red edge, okay? That's the case without noise, everything is correct, it's like connected correctly. Good. So now I'm introducing single label noise. So what I do, remember, when I have introducing single label noise, I just flip, I mean, the label of one of the samples, right? So here I have the orange and I call the orange red, I call the orange black. And what the neural network has to do to adapt is basically to move, right, to this circle now. Now they are connecting this graph here. So this is, I mean, pretty much similar to the way, the situation here, right? The neural network has somehow to adapt. Basically just, I mean, the easiest thing it can do is just to move this, I mean, orange to close to this graph of black circles here. However, now if I have pair label noise, what I'm doing, I'm taking like a black circle and an orange circle that are different, and I call it now similar. I take like, let's say like comparing with the no-noise case, I have a black and orange that are different. I mean, if this is correctly labeled, and then I call it like, okay, they are equal. And you see, by doing this, I'm introducing inconsistency in my data set, because I just say this is equal. Now I say this is equal. But of course, now this is different. So this is just inconsistent. I mean, this, of course, there is some inconsistency that I'm introducing by forcing this noise. And again, I repeat this again. I just take like this edge here that is correctly should be correctly labeled as similar pair. But then I call it different. And again, you see that I have introduced some inconsistency in this gray area here. Like this is now, okay, they are similar and I call it different, but now they are different again. So there is no way to let's say that I'm breaking completely the transitivity in this graph by introducing this noise. And this is because no matter how many parameters we introduce, there is no way you're going to overfit and completely explain this, because by introducing this breaking of transitivity in the data set, we are actually introducing some break of similarity. And then we call this like a density-induced break of similarity. This was our interpretation of what's going on. Of course, this is a really high dimension, and we don't have like let's say, analytical explanation for the kind of super high dimension space that we're considering here, but we actually can recover exactly a formula where we go in the limit of the infinite data, we recover exactly the amount of error that we expect in this plot here. Okay, so I'm getting to the end already. So, so today I try to stress a lot this phenomenon, like double descent phenomenon. That's not well explained in the literature yet. We are trying to explain it. And what I really want is, in general, to highlight that there is this big gap between what we understand, like what we can explain with the theory side, and what is known in practice in deep learning. And I think if we really want to expand the scope of machine learning applications in the science, in industry, but if you really want to trust these tools, you really need a theory for deep learning. And today I focus on this side, right? Like the phenomenology of deep learning, but there are like many other ways, many other opportunities to explore, right? There is, as you know, the physics-informed neural nets, where you give already some information about the conserved quantities that you have in your system, so the neural network doesn't have to learn from zero. There are a lot of people work on this interpretability side, that this example of the Lorentz transformation that I said at the beginning. And there is this also very nice analogies between randomization group flow and the depth of the deep neural network that I think is quite nice. So yeah, I guess I'll stop here. Yeah, what I have to say. Thank you very much.
Thank you very much, Nayara, for the nice presentation. It's time for question, comment. Anybody?
Can I ask a question?
Yes,
Yes, of course.
I was looking for the raised hand, but I was not finding it. So thank you very much, Nayara. It was really, really nice, amazing, your talk. So I have a question about this phenomenon of the double descendant. Super interesting. So is this happening for every model, every machine learning model, or is just something that happened on neural networks? I mean, do you know if this happened also for any other models, or even for simple example, I mean, for a polynomial, it also happened for a polynomial, or?
It happens for like these Random Fourier features that are basically like a kernel when you can fit like, basically I mentioned here, these random features that is not even a neural network, it's a pre-neural network. Let's see where I have it. Yes, this also happened for this kind of model, like a random Fourier feature that just like you think like I have a 2-layer, one layer is not trainable. So it's really like kind of a regression, a more complicated way to do a regression test. But this also happened there. This is what they explore in the original paper, the descent paper. They have just very simple. I mean, here are like plots for the original paper, and they are just like using very simplified neural networks, and even like these kernel models that are just like prototypes of neural networks. So indeed, it also happens there, and there it was even like really like the peak. It's even higher for the simplified version. So. Yeah, it's kind of weird. What the surprising thing is that people said, okay, this also happens for deep nets and also happens for deep nets, right? That's what it comes later. But the original paper, they treat more simplified, like a regression. This happens for regression, for instance.
And for a polynomial, for example, It would
because
happen?
if
Maybe
you try,
something.
yeah, for a polynomial, you say like it would be hard to fit something better, right? If you have already, if I give you exactly the formula, right? So if you give more parameters, I guess it would be hard to fit something any better if you give the exactly formula. I don't think it would work. Maybe, I guess, probably this also could happen, right? This kind of situation, but I don't think this is going to be as lower as this, right? I guess probably in this case, right? In the case of the polynomial case, probably the sweet spot is really here. This is the best you can do it. Probably after you increase a lot the number of parameters, you also reduce again, but not as good as here, right?
I see.
I mean, what the surprising thing here is that you see, like this point far away is actually better than sweet spot. And this is kind of a weird, right?
And this is without using any regularization technique.
No regularization. Indeed, that's the thing here.
Okay, thank you very much.
Viviana, go ahead.
Yes. Thank you. Thank you, Nayara. I have actually a very basic question. I don't know if you have defined it and I lost it or no. How you define the error on the train error? So I understand the error on the test, but how you define?
It's just like, let's say this simple example here would be just the point, right? The y-axis as a function minus the prediction. So this would be for like a test and train, right? Exactly the same. Just the test I'm not showing, right? Test would be like the new data that I'm putting here, extra samples. But I mean, this is one example of mean square error. There are the way we consider we actually using the contrastive loss. That's something more complicated, but for the mean square error, it's just this, right? I'm just comparing the true, let's say the true label, that's the value, in this case, the y here, with the prediction.
Okay, maybe I'm biased because I'm working on neural network, but not deep neural network. So in that case, we have our set of data and we share it in the training test and the test set, and we define the occurrence in this way and the error. So in this case, you don't have this kind of separation? Or
no, indeed. Yeah, I'm training just like during training, I just, my model just sees the training set, right? Just the training set. And then by the test is something that the model has not seen, right? You just like, I just show later, and then I compare again, right? With this. And that's why, I mean, at some point we expected that this is going to be worse and worse, right? Because there is no way to, I don't know if it's exactly the same. If you're using like a neural nets or deep neural nets, it's just a measure. The training is like, is what the model sees, right? And then we just show new data, complete new data for the test set. I don't know if it answers or you repose about.
No, you answered that, and I don't know. It's still not clear to me actually. But
just
maybe it's something like in my, I don't know, understanding.
Yeah, maybe just like you say the accuracy is just 1 minus, right, my error, right? If you want to convert this to the accuracy, it's just like the accuracy would be just like the error, like the 100% minus the error. That's the accuracy of your model. Basically, if you want to convert this plot, like here, I'm just like the error that I'm making, but I can convert to the accuracy. So it means like here that I have 0 error means I have 100% accuracy, right, in the training.
No, okay, yes, I got it now.
That's
Thank
it.
you.
Yeah, that's
Thank
it.
you.
Maybe, yeah, I guess sometimes people present it with like the accuracy, and we're usually, I don't know, for some reason people start to presenting this like the double descent with the task error, but yeah.
No, because I was thinking about the same number of parameters, but of course, if you change it, you can define both. Yeah, sorry, that's fine. Thank you.
No problem. Thank you. The question.
Martin, do you have more questions?
Yes, I mean, if there are no more questions, I can
go
continue
ahead.
asking. Okay, so
yes, sure.
I was wondering if it is the same of adding new neurons in a hidden layer or adding new neurons in the last layer.
Yeah, this is an interesting question.
Yeah, because I found a paper, it's a quite old paper, but I found it like last month, that they talk about this like effective number of parameters in neural networks. And they say that are not equal to, I mean, the effective number of parameters that you have to take into account in this kind of statistical sense are only the last layer parameters or something like that. So that's why
this is, this is totally true. In principle, for the, let's say, for this classification test here, they have fixed here they have 10 classes, so they fix like the last layer as with 10 nodes, right? And then they apply like a softmax there. But what people do, because indeed we know, we already know this, that depending on which layer you change, this change different things in the model. So the way we do here and what people do to test this kind of phenomenon is just to increasing layer by layer, right? Just the hidden layers, that we think they are the less sensitive, right, to what we're doing. We increasing the number of parameters. Let's see, I have here okay, here, right? Just increasing here in the middle, like the hidden is the number of nodes. But indeed, I mean, because we don't want to exactly probe this kind of thing, right? We don't want to be sensitive to, like, let's say, change the output or things like this. But in principle, one can change, one could do it. Yeah.
Maybe I explained wrong. Yes, I was not referring to exactly to the last layer, but the last hidden to the last layer, let's say.
You mean not the output, like something like...
Yes, not exactly the output, but the previous layer. So I read this paper that they said that indeed this was like a special layer, like all the hidden layers were like just making like a transformation, a nonlinear transformation to your data, and was just the last hidden layer, the last hidden layer, let's say, the one that was important for this kind of analysis. So that is the real question.
No, I see. We didn't try this. I mean, in principle, I really don't know if we just move, let's say, just change the parameters of this, like the last hidden layer, let's say, right? I don't know what's going. And in general, when people do like this double descent experiment, they change all the hidden layers. Like they start to increase. They, let's say, increase the parameters uniformly, right? But I guess we can also play with this and see what happened. But yeah, we didn't try. But yeah, it's for sure it's a valid, valid thing to try.
Great. Thank you.
Okay. More questions or comments? No. Okay. Then it's time to finish. Thank you again, Nayara, for the nice seminar.
Thank you. Thank you very much for the questions.
We stop the recording.
Thank you.
Thank you.